Hi there. This is John Vise for Edinburgh Explorations. That's what I'm calling this show where I talk about math and physics and other sciences maybe and interview people and things. So I was trying to lose weight recently. I just don't quite know how to do it. I was thinking about what's the best way to lose weight. And I realized that if I went to the moon, I could lose a lot of weight. In fact, my weight would be just 1/6 of what it is now if I was on the moon, because the force of gravity is so much less there. But then I realized that wouldn't actually be what I really wanted, because it's still just as hard moving around in a lot of ways, even when you have less weight. What I really wanted to get, I realized, was less mass. I want to lose mass, not weight. Mass and weight are proportional to each other on the surface of the Earth, but anyway, I want to lose mass. So I was going to a donut shop and thinking about this when I saw this glass case, weird glow on the bottom of it, and it had some donuts in it. And there's a sign on it saying negative mass donuts. And I got really interested because I realized that if I ate negative mass donuts, I could actually lose mass. So I opened up the case and I tried to grab one of the donuts, the one on top, and something really weird happened. I grabbed it and I tried to pull it towards me, but it slipped away in the other direction and it fell off the case. It fell onto the floor, but then something even weirder happened. It hit the floor, and then it started like pressing down into the floor and sort of disintegrating, and it punctured a hole in the floor and just like broke into tiny pieces, and they all went down through the floor. And the guy who owned the shop said, "Hey, what did you do? You weren't supposed to just grab a negative mass donut like that. That doesn't work." And I realized as soon as he said it that it was ridiculous for me to grab it like that because you see, Newton's law says that force equals mass times acceleration, right? And that means that if you push on something with a force, then that's equal to the mass times the acceleration. And if the mass is a positive number, and the force is pointing this way, then the acceleration will be in that direction too. And that's the usual situation because mass of most things is positive. But with this negative mass donut, when I was pushing out at a force in one direction, namely trying to grab it, it accelerated in the opposite direction. So it slipped out of my hands like that. But then I got really confused because if the force is pointing one way, then the negative mass donut accelerates the other way. But, but why didn't the force of gravity work like that too? Right? Gravity usually pulls objects down, ordinary positive mass objects that go accelerate downwards. But wouldn't a negative mass donut accelerate upwards in the opposite direction? And so I asked the guy at the shop about that. And he said, "No, you idiot. Don't you remember Newton's law of gravity? Newton's law of gravity says that if you got two different masses, it tells you how to figure out the force between them. And so what you do is you take the mass of one object times the mass of the other object, and you divide by the square of the distance between them, because gravity gets weaker when they're further away. And then you multiply by some number called the gravitational constant. But normally that force on both those objects is also pointing towards each other. So each object is accelerating towards each other, or the forces towards each other. And so that's Newton's law. The force is the gravitational constant times the mass of the one times the mass of the other divided by r squared, and that's the force pointing inwards. But if one of your objects has negative mass, then that formula gets an extra minus sign in it. So then the force on those objects actually points outwards. So if you've got an ordinary positive mass object and a negative mass object, the gravitational force on them points outwards instead of inwards, because you've switched the sign of one of those masses. So you see my negative mass donut, instead of feeling a force downwards like you normally expect, it was actually feeling a force upwards, the opposite direction, because of that negative mass. But then, because of Newton's law, force equals mass times acceleration, also has a mass in it, also has the donut's mass in it in this case. That extra minus sign means that although the force on the donut from gravity was pointing up, that the donut accelerated down, just like a normal donut. So there are two minus signs you see in how the donut accelerates under the force of gravity. The force switches sign if it's a negative mass donut, but the acceleration also gets an extra minus sign because of F equals ma. So it still accelerates downwards as usual. So it fell down, it hit the floor. Now, normally the floor holds up the donut, right? Because the floor has a force pushing upwards on the donut. But for this donut, because it's a negative mass donut, that force upwards translates into an acceleration downwards. So the donut actually accelerated downwards into the floor, even though the floor had a force up. And the more the donut tried to accelerate downwards into the floor, of course, the floor gets pushed down, the floor was pushing back up with even more force. And so the donut accelerated down even more, and the donut basically drilled its way into the floor. Of course, since the donut was just made out of some weird negative mass flour, it disintegrated under the force of all this, but it's still, all those pieces have negative mass, and they just drilled their way down into the floor. So I lost my donut, and I had to pay for it anyway, which is the worst part. But it got me to thinking about negative mass, and well, I'll let you figure out how the store actually managed to have a glass case of negative mass donuts and not have it fall through the bottom of the case. It was a special case, you see. I should have realized that before I even tried to grab the donut. Anyway, so negative mass, it's sort of weird, right? One thing you've noticed is that mass shows up twice in my calculations of Newtonian physics here. There's the first time, right, in the law F equals ma, the relationship between force and acceleration. That mass is called inertial mass. That usage of mass is called inertial mass. And then secondly, when you're figuring out the force of gravity, you take Newton's constant times the mass of one object times the mass of the other, divide by the radius squared. Those masses in there, that's called gravitational mass. Now, we normally think that inertial mass and gravitational mass are just the same thing, so we don't usually call them by different names. But at some point, people realize that theoretically, they might be different. And you should actually do experiments to see if inertial mass is always equal to gravitational mass. And people have done, in fact, lots of experiments, and they found that, yes, it's true. Inertial mass always seems to be equal to gravitational mass. And actually, Einstein's theory of general relativity predicts that inertial mass has to be the same as gravitational mass. So we pretty much believe that that's true now. So you might have fun figuring out for yourself if you had a donut that had, say, positive gravitational mass and negative inertial mass, what would it do? Or the other way around. They're fun to think about. Or, yeah, so different things like that, variations on that theme are really a lot of fun to think about. But when you're thinking about weird things like negative mass, it's important to realize that physics lets you do calculations of what's going to happen when you work within a theory of physics, but you got to pick a theory of physics to do your calculations in. You can just not pick any theory of physics and then you're just like thinking about stuff. And you may be good at it and you may be bad at it, but it's sort of hard to tell when you're right and when you're wrong, especially if you're talking about really crazy things like negative mass. But if you pick a particular theory of physics, like Newtonian mechanics, then if you say something crazy like, hey, let's suppose mass is negative, you can just do calculations in that theory and you can figure out what will happen. And as long as your math is right, you're doing a correct calculation. Whether it's related to the real world is a whole separate question. And it might not be related to the real world, but at least you're playing a game that has definite rules. You're not just making stuff up as you go. So you can say definitively that in Newtonian mechanics, when inertial and if inertial and gravitational mass are the same, and you've got a negative mass donut, it'll fall down. I mean, so that's a calculation using the assumptions of Newtonian mechanics. And so if you're going to think about negative mass, you can do it using Newtonian mechanics, but it's fun to think about it in other ways too, because Newtonian mechanics is by no means the last word on physics. There are various theories of physics that are quite successful, and some of the biggies are Newtonian mechanics, and then special relativity, where we take into account the fact that the speed of light is very special. Nothing can go faster than the speed of light. And also that there's no way to tell whether you're moving or not if everything was moving along with you. And then there's general relativity, which I briefly mentioned already. It's like a generalization of special relativity that takes gravity into account, describes gravity as the curvature of space and time. And then in the different direction, there's quantum mechanics, where you take into account the fact that there are pairs of things that you can't measure both exactly at once, like you can't know something's position and its momentum both perfectly at once. And then there's things like special relativistic quantum mechanics, usually called relativistic quantum mechanics, where you combine relativity and quantum mechanics. And then there are fancier things like quantum field theory and so on. So you can think about the question of negative mass in any of these different frameworks. And it's worth thinking about a little bit because you might get some insight into why there are no negative mass objects, for example, negative mass donuts, some practical application of that. Um, so, so like I said, in Newtonian mechanics, negative mass is perfectly allowed. It just behaves in weird ways. And you may say, well, that's so weird, that's never going to happen. But that's sort of your decision, or that's an experimental observation that like we never see anything fall up. So therefore, there are no negative mass objects in the framework of Newtonian mechanics. But we might hope that in some of these other more fancy frameworks of physics that are actually more accurate, we could see why, from those point of view, those theories' point of view, why there are no negative mass objects. So for example, let's look at special relativity. That's a really interesting one to think about. So you've probably heard this equation in special relativity, E equals mc squared. Energy of an object is equal to its mass times the speed of light squared. This is sort of the most famous equation in physics, maybe after F equals ma. Maybe it's even more famous. It's certainly the most famous equation associated to Einstein. But Einstein actually never wrote down that equation in his famous papers on special relativity from the year 1905. Um, and it's interesting that he didn't. So we'll see actually that that equation isn't exactly right. Maybe that's why he didn't bother writing it down. It's right in a particular case, but it's a little bit misleading, actually. So let's think about it a little bit. So first of all, why is it E equals mc squared and not E equals mc cubed or E to mc to the fourth or equals mc or something else like that? There's actually a funny cartoon by Gary Larson where Einstein is sitting dejectedly in his office, and on the blackboard he has E equals mc cubed, and it's crossed out. E equals mc to the fourth, that's crossed out. Equals m, crossed out. You just can't figure it out. And then the cleaning lady, who's just finished cleaning his room, says, well, I got that squared away. So it's a silly cartoon. Well, cartoons are supposed to be silly, but I'm a serious physicist. That's a silly cartoon because Einstein would have known right away that none of those other equations had a chance of being right because you see, in physics, we use something called dimensional analysis. We say that each quantity, like energy or mass or the speed of light or whatever, has some dimensions, which are products of mass, length, and time, and their inverses. And the equations only make sense if the dimension of the stuff on the left equals the dimension of the stuff on the right. Because if it weren't true, then if you changed your system of units for measuring length and mass and time, the equation wouldn't be true anymore. I don't want to get too much into dimensional analysis, but you see energy has dimensions of mass times length squared divided by time squared. Why is that? Well, for example, energy in Newtonian mechanics, the energy of something due to its motion is called its kinetic energy, and the energy of something is 1/2 the mass times the velocity squared. 1/2 has no dimensions. It's just a number. Mass has dimensions of mass. Velocity has dimensions of length over time. So energy has dimensions of mass times length squared over time squared. So since energy has dimensions of mass times length squared over time squared, then if you're trying to write down some equation like E equals m, what? Well, that other thing has got to have dimensions of length squared over time squared to make it match up. And if you know you want the speed of light to be in the game, and special relativity is all about the speed of light, then the obvious thing to stick in there is the speed of light squared, because the speed of light squared has dimensions length squared over time squared. So E equals mc squared makes sense dimensionally, whereas E equals mc cubed just would not make sense. If it were true in some system of measurement like meters and seconds, it would be false if you were using like feet and seconds, which would be weird. It would be ridiculous to have a law of physics that cared whether you're using feet or meters. Anyway, I don't want to get too much into dimensional analysis, although it's tons of fun. My point is just that the brilliant part of E equals mc squared is not the c squared. It's not the squared part. It's the idea that energy and mass are two aspects of the same thing. And then if you're working in a theory where the speed of light is the main big deal, then it's going to be equals mc squared. So in fact, people working on special relativity, they often like to pick a system of units where c, the speed of light, is equal to 1, so that you can just stop worrying about it so much. So for example, if you measure distance in light seconds, that's the distance light travels in a second, then, and you measure time in seconds, then the speed of light is, of course, 1 light second per second, and it's just 1 light second per second. So in that system of units, the speed of light is 1. So c equals 1. And then you can just sort of relax temporarily, as long as you know what you're doing, and you can just say equals m, because c squared is 1 in this system of units. It's only good in that system of units, so you got to be careful. But if you're smart, you can realize whenever you need to that you can stick the c squared back in there. So people who do a lot of special relativity just set c equals 1, and they know what they're doing, hopefully, and so they can just say equals m. So let's do that, okay? Let's let the speed of light equals 1 for the rest of this conversation here, okay? Because I'm talking like people do in special relativity. But my real point is this equation equals m is oversimplified. It's not the real equation that matters in special relativity. It's a perfectly fine equation if you have an object that is not moving at all. But if you have an object that's moving, it's not true anymore that equals m. More precisely, if you have an object that has any momentum, momentum is sort of some kind of measure of how much something is moving along and how big and hefty it is. If something has some momentum, then it's not true that equals m. So I got to tell you what's the real equation. So the true equation that you learn when you get deeper into special relativity. And I'm going to using these units where the speed of light equals 1, okay, to keep it really simple. So the equation is this. It's m squared equals e squared minus p squared. Let me say that in English. What the hell is p? P means momentum, okay? So what I'm trying to say in plain English, or something more like plain English, is energy squared, sorry, try again. Mass squared is energy squared minus momentum squared. Let me say it again, okay? Because I screwed up the first time. Mass squared is energy squared minus momentum squared. So when the momentum is 0, you just say mass squared is energy squared. And if you take the square root of both sides and you relax about the minus signs, then you just get mass and energy are equal, okay? But notice that you took a square root. Remember how the teacher always said, you got to worry about the minus signs when you take a square root. So we'll get back to that. But the real equation here, right, is mass squared is energy squared minus momentum squared. And what's cool about that, what's important about that, is that the mass squared doesn't change if the object you're talking about starts moving. So if you have an object that's moving, its energy gets bigger, so energy squared gets bigger, but also its momentum gets bigger. So when an object like a donut starts falling, its energy squared will be bigger the faster it moves, and its momentum squared will be bigger too, but e squared minus p squared, believe it or not, stays the same. So in fact, e squared, energy squared minus momentum squared is the only thing basically that stays the same, no matter how an object is moving. It's the only thing that stays the same that you can cook up from energy and momentum. So it's an incredibly important combination of the concepts of energy and momentum, e squared minus p squared. And so it deserves a name. Well, it has a name. It's mass squared. So mass in special relativity has a new meaning, a different meaning than the meanings that we saw in Newtonian mechanics. We could say that mass squared is the quantity that you can measure about an object that depends on its energy and momentum that doesn't change if the object is moving. So it's what we call an invariant, something that doesn't change when you do something, in this case, set something moving. Now, here's the kicker, though. That's a formula for mass squared. Mass squared is energy squared minus momentum squared. It doesn't tell you what the mass is, it only tells you what the mass squared is. In this branch of special relativity, and in a lot of physics connected to special relativity, though perhaps not all of it, you never care what the mass is, you only care what the mass squared is. And so that's really weird and interesting because it means that this whole question of negative mass sort of is moot, because if you replace mass by negative mass, when you square the mass, it doesn't change, right? When you stick a minus sign in front of a number and then square it, the minus sign doesn't affect the answer because you get minus minus, which is plus. So what I'm saying here is that if you dig into special relativity, it tells you a deep new understanding of mass squared as this invariant quantity that doesn't change when an object is moving, but it tells you nothing, that at least tells you nothing about mass. It doesn't tell you whether the mass is positive or negative. We just always pick it to be positive because you got to pick one or the other, and positive just seems less weird. But that's sort of interesting because it sort of suggests that it's an arbitrary convention that we've chosen the mass to be positive in that context. Now, that's not the last word on the story either. Special relativity is all fine and dandy, but it doesn't take gravity into account. When we try to bring gravity into account, then of course mass has some kind of new significance because, very naively speaking, mass makes there be gravity. We already saw that in Newtonian mechanics. So Einstein invented general relativity to get gravity into special relativity. And there's a new way of understanding mass in general relativity. And I don't want to get into it too much because it's getting too long already, but there's a theorem called the positive mass theorem that says that if you've got any object or bunch of objects in some confined region of space, then you can measure its mass from far away by like orbiting something around it and seeing how fast that thing goes around. And that concept of mass is mathematically very interesting. It's called the ADM mass. And the theorem says that that mass is always going to be positive if this matter that you're making your objects out of is not really weird. So there's a condition called the dominant energy condition, which basically rules out strange stuff like tachyons, and all normal matter obeys it. And if you got this dominant energy condition, you can prove that the mass, or so-called ADM mass in general relativity, will always be positive. So that's like some argument that that mass should be positive in general relativity. If we combine special relativity and quantum mechanics, we get something very interesting called relativistic quantum mechanics. And there we learn something really beautiful. We learn a kind of classification of particles according to their properties. And one of their properties is the mass, but actually it's the mass squared that counts. Only the mass squared shows up. So it's like what I was saying about special relativity. And if the mass squared is positive, that's normal matter. So ordinary matter is made of particles where the mass squared is positive. If the mass squared is zero, that's also allowed. And there's only one particle that we know that has the mass squared being zero, and that's a photon. Of course, if the mass squared is zero, the mass is zero. So a photon, or the particle of light, is a massless particle, and it moves at the speed of light. It's a feature of massless particles that they move at the speed of light, whereas ordinary matter moves slower than light. And then also there's another theoretical possibility in relativistic quantum mechanics, which is that the mass squared could be less than zero. Now, the mass squared being less than zero is completely different than negative mass. This is negative mass squared, okay? And so if you have a negative number as the mass squared, it actually means that the mass is a square root of a negative number, and that's imaginary number. That's an imaginary number. So this other possibility I'm talking about now is perhaps weirder than negative mass. It's imaginary mass. And this possibility, which is there in relativistic quantum mechanics, uh, is called, well, a particle with negative mass squared is called a tachyon. And there's some sense or other in which it moves faster than light. I don't want to get into the details of that because that's like rather tricky, but basically it's at a simplified level, it's mass squared is positive for ordinary matter that moves slower than light. Mass squared is zero, that's moving at the speed of light. And there's only one example we happen to know, which is light. Maybe gravitons also move at the speed of light, though we haven't seen them, but I believe in them actually. But we haven't seen them. And then the third possibility, mass squared is less than zero. Those are called tachyons. We've never seen any sign of those, and those move faster than light. But you'll notice that in all this wonderful classification of particles in relativistic quantum mechanics, we're not talking about mass, we're talking about mass squared. So when m squared, the mass squared is positive, it doesn't tell you whether the mass is positive or negative. You could take the square root, but you can get a positive square root or a negative square root. So basically, this whole theory of relativistic quantum mechanics, it doesn't give a darn whether the mass is positive or negative. So you might as well just say it's positive. So as you can see, the whole business of negative mass is pretty tricky and complicated, and I got interested in it actually when I was reading about some new research where some people were arguing that experiments in cosmology favor the possibility of neutrinos having negative mass. But actually, if you look into that stuff carefully, you see it's a little bit of a misleading description of what's going on. If you look at the math, you see that there's nothing in there that's really saying that the neutrinos have negative mass. It's a bit of a long story, but it got me interested in the whole business of negative mass. And I really wish there were negative mass because I just don't know how to lose weight. If someone could ever tell me how to lose weight, I'd be really interested. And so my whole idea of doing it by eating negative mass donuts, it just doesn't seem to work. Okay, great talking to you. See ya.